Welcome to today's webinar, The Challenge of Thermal Decarbonization, brought to you by Armstrong International. My name is Steve Ashby, Director of Global Food and Pharmaceutical Markets for Armstrong, and I'll be your host today. I have over 23 years of service to Armstrong International and to our customers, the last 5 of which in the capacity of Market Director. And it's a pleasure speaking with you today, and I'm glad you decided to take an hour of your time to be with me. You can see my contact information there, sha@armstronginternational.com. Please feel free to reach out to me at any time. And I've also listed my cell phone number. So I like to talk to people in person, so please give me a call at your convenience and we can discuss anything about Armstrong, and most certainly we can discuss today's topic. A couple of housekeeping notes. Today's webinar will be approximately 1 hour in length. Everyone is muted, but we do have a way for you to communicate either through our chat function or through our Q&A. So if you have questions, please submit those and we will address those at the end of the webinar. Today's session is being recorded and will be available on our Armstrong YouTube channel. And if you're not already a subscriber, please subscribe to Armstrong YouTube. Lots of great information on there, lots of nice case studies and information on our products and services and applications in covering various Armstrong methodologies. And we do recommend that you do close any background apps or browsers. Sometimes they'll affect the streaming quality, and we're hoping today's presentation comes through clear for you. For those that don't really know who Armstrong is or know a little bit about us, let me give you a little introduction to who we are. We were founded in 1900 and we're a 5th generation family-owned business. We consider ourselves a global leader in energy management. And more importantly, although we're global, we're managed as one global P&L. So we have the reach to affect plants in the Americas as well as Asia and in South America to be able to provide the same level of service and product technologies as we do here in the United States. We're headquartered in the US with manufacturing, service, and training centers located throughout the Americas, Asia, and Europe. We do provide integrated solutions, and our solutions have developed over time that will help you save money, energy, and save time in your processes. We consider ourselves a trusted thermal partner, utility partner to customers all over the globe. More than 100 countries consider Armstrong a trusted advisor for them. Most importantly, though, is we want you to be happy dealing with Armstrong. So we expect enjoyable experiences. So we want to develop that level of relationship with our customers so that you're happy with what it is that we do and the service and products we deliver. Our global presence is shown here: manufacturing, sales, and service. The gold dots represent our primary manufacturing centers, and the black dots represent our other services and manufacturing centers for some of our auxiliary equipment that we manufacture and sell to our customers throughout the globe. Industries we serve range from hydrocarbon chemical processing, our HPI, CPI customers, certainly the food and beverage and pharmaceutical market, hospitality and government, healthcare, power, and many others take advantage of the services and products that we help, and we certainly help those customers improve their thermal networks. So today we're really talking about, if you have established how to reach your net zero goal. It can be quite a complex journey. It can take us all the way to decarbonization. And as those technologies evolve over the next 10 to 15 to 20 years, those will become a more commonplace and customers will be able to reach that full thermal decarbonization. But in the meantime, we need to take a look at what we do now. And that's really our circular thermal approach. And it really revolves around optimization, minimization, and heat recovery within our current processes. So again, challenging part of this is I'm looking at my scope 1, scope 2, scope 3 emissions. And we know that some of that will take place in the future as many of our customers are setting decarbonization net zero targets of 2040 and 2050. But what do I do now? Well, we're going to take a look at those scope 1 and scope 2 emissions, which do or can be thermally decarbonized, and those represent 2/3 or 60 to 70% of your total scope 1 and 2 greenhouse gas emissions. That's what we can address now. That's what we're going to take into account as we move forward and start on our journey. So our journey really begins with optimizing. And that's the thermal network total efficiency. That's taking account for all heat recovery, all of the waste that's generated, using that to generate heat or primary energy in our plant. Minimizing the process energy demand, that is something that we would ask our customers to take a look at. That's challenging your equipment that you have, your heat exchanger networks, your process equipment, your OEMs, to deliver more and better efficient equipment. And then take a look at lowering set points where practical. Do we generate hot water at 180 degrees only to use it for 30 minutes in the morning? The rest of the day we use 140 degrees? Why don't we take a look at generating at 140, reduce the primary heat demand that's needed, and then look at heat recovery to boost those temperatures up to those process needs when and where they need them. And then the last piece of this puzzle is decarbonize. We can certainly hit an easy button, electrify everything, but that'll have a negative impact on our operating expense and our capital expenditure. And we'll take a look at that as well. But that's the end goal. Many, not all, many of our customers are looking to get to. But we do know our thermal networks will need to become much more flexible to handle multiple inputs, both from primary generation and from our heat recovery process, to deliver the ultimate goals. So they'll become much more complicated. They'll need to be much more flexible. So if we take a look at what we would say is a typical thermal system, we have our primary energy, our natural gas, or perhaps other fuels, biogases, that being used now to generate steam, to generate hot water. We have electricity to power our CHPs, chillers. All of those utilities generation are producing waste heat, whether we're sending processed water back to or condenser water back to a cooling tower, wasting heat up the boiler stack, or taking heat from our processes and venting that out to atmosphere. But our utilities generation is delivering our steam, hot water into our thermal network, which then goes to our thermal users. Our building heat, humidification, process cooling, process heat, all of those are generating waste heat as well. But we do know many companies are good at and do have some direct heat recovery, both from the utility generation, stack economizers, or from direct heat recovery, water to water, air to air, type heat exchange recovery, and delivering that back into our thermal network. But there's still quite a bit, large amount, that's still being vented to atmosphere that we need to account for before we take a look at what's best or how we're going to decarbonize our facilities. So if we look at circular thermal, this is our message. We're taking an average plant, we're taking into account the atmosphere, the region it's in, how warm it is in the summer, how cool it is in the winter, and we know there's going to be a degree of heating, and we know there's going to be a degree of cooling. So we typically look at 20% or so is the amount of the electricity typically we need for our cooling applications or cooling refrigeration. And in a circular thermal approach, we take a look at what is cooling. Cooling's about extracting heat. And we know that through our condensers and our chillers, that we're going to produce a certain amount of low-grade heat that is often sent to cooling towers. And we know that cooling towers typically can represent water consumption, quite a bit of water consumption, up to, let's say 10,000 cubic meters per year per megawatt. The rest of that comes in the form of generating heat. And the primary fuel typically used today in a lot of areas, especially North America, is natural gas. We're producing steam just above, say, 15 psi, going to be greater. Certainly we're generating at higher pressures, but we have steam at 356 F. Some of that steam is used for high-grade heat above 250. Some of it's used for direct injection onto a product. 30% of that might be used to generate low-grade heat, temperatures below 248 degrees. 50% of that, though, very large a quantity, is used to generate hot water. And that hot water generation is typically below 176, let's say below 180 degrees. So we're using a lot of energy to generate low-grade heat. And when we look at, and all of those processes certainly are sending waste heat to grade. So when we look about heat, heat's about adding heat. Cooling is about extracting heat. That's the circular thermal approach. So we take a look at our factory. We still have our cooling and refrigeration requirements. We're going to take a look at, yes, we're a steam company, but we're going to talk about de-steaming, using heat recovery, reducing the amount of steam we actually need, and looking at that 20% or so that's required to generate our high-grade heat for our processes. And 80% of that are become hot water networks, delivering low-grade temperature heat below 248 to our processes. So we'll look at direct heat recovery. We'll look at recovering the cooling aspect, the heat out of the water we're sending to the cooling towers. We'll do that through heat pumps. And we look at that through, we know we're going to need electrification. So we know that if we're purchasing renewable electricity, our electricity requirements might be increased by, let's say, half. Conversely, though, since we're looking at renewable technologies in the future to generate our heat, we're looking at heat recovery. We're going to decrease our thermal load by up to 3/4, that 60 or 70% that we talked about earlier. But important thing to remember is that our total energy to process is going to remain the same. We're not starving the system, but we're utilizing all of the heat in the system to reduce the amount of primary generation we need to have. So taking a look at an example of what that factory might look like in the future. Along the left here, we still have all of our generation sources. Green gas supply for biogas boilers, biomass, perhaps hydrogen in the future. Electricity, green electricity to fire electric boilers or electric steam generators. Solar thermal delivering low temperature hot water generation into our network. Air, ground source heat pumps, absorption chillers, water chillers, our dry coolers, all taking a green electricity, all delivering that utility out into our processes, our air handlers, our air conditioning units, our processes. We're going to take then those heat loads and put those back into the system through heat pumps. We'll take the steam, the high-grade heat off of our processes. We'll combine that with recovered heat from our chillers, take that into industrial high-temperature heat pumps to raise that temperature above the pinch, to deliver that hot water up to 248 degrees Fahrenheit into our network, to take care of 80% of those heating needs that are low-grade heating needs. And then we'll use direct heat recovery from many of our other process streams through air-to-air, water-to-water heat exchangers to provide heat to HVAC units. So the example of the factory of the future is going to be green generation with heat recovery in the process. So it's quite unique, quite complex, but we can break that down into what we focus on today is where we start, and that is with heat recovery. So the thermal decarbonization and journey, we break it down into that optimize, minimize, and decarbonize. And optimize, certainly those technologies currently exist today. Technologies that'll improve our steam systems, that'll allow us to de-steam, heat pumps, direct contact heaters, direct heat recovery through those technologies. And those we take a look at, and the solutions impact on those is we're going to see a reduction in our CO2, our greenhouse gas emissions. We're going to reduce our energy consumption. We're going to help you become more profitable. We're going to help you and find ways to reduce your operating expense in these technologies to optimize with a slight increase in your CapEx requirement. Minimization, that's where we're asking you to take a look at and challenge your processes. Many of those technologies exist today. They're what you buy from your OEMs. Those are going to improve efficiency. They're going to decrease the carbon intensity of your processes. So they'll reduce the CO2. They'll continue to reduce your energy. They'll continue to drive your operating expense down as you become more efficient with a relatively neutral CapEx requirement because that funding is going to be there. I say it's going to be there, but that funding is going to be there as you replace equipment. As it reaches its end of life, you're going to budget for those type of replacements. But when we look at decarbonize, some of those technologies that are widely applicable today include electrical boilers, steam hot water, shallow well geothermal, carbon capture, and then locally, region dependent, or even locally dependent biomass, biogas, biomethane to help drive our primary energy and the heat generation. But some of those technologies are evolving. They're 15 years away, okay? We could hit the easy button and say, we're going to electrify everything, okay? Great. That'll drive our CO2 emissions to nothing. We'll be zero. We'll be a green facility. Our energy consumption will be fairly neutral, really no impact on that. We're going to drive our operating expense up because in most places, electricity is certainly more expensive than natural gas. So our operating expenses are going to drive upwards. And then our capital expenditures, though some of those technologies can be more expensive today, that's going to drive our OPEX costs up with very little then on the ROI part of it. So we see a future in all of this. But if you had to ask, then we would take a look at where do we begin? And that's going to be in that optimize and minimize. Let's take use of all of that heat recovery. Let's challenge our processes, get ourselves to a baseline of efficiency where we're recapturing a lot of the energy, the heat we're already producing. Then take a look at decarbonizing that remaining thermal generation. And if we look at thermal decarbonization by industrial process, again, I mentioned earlier that 2/3, 60 to 70% of the thermal decarbonization is going to drive those scope 1, 2 into energy, those emissions reductions. So shows here in this chart where our minimize, optimize, decarbonize. Again, we're holding true that how much we're going to be able to reduce by optimizing our systems first. So how does Armstrong help you, or how can we help you on your journey? Well, we'll take a look at thermal mapping is a great place to start. So we'll call thermal mapping and pinch. What we know and what we've learned in the decades we've been helping our customers, but more notably and most recently on their decarbonization journeys, is a lack of reliable data about their system. And that has to speak primarily to flow measurement and the lack of flow measurement devices in the plant and understanding where all of that energy, where all those flows are being used, time, temperature, location. All of that is critical to understanding our system, understanding where we can recover heat, to come up with a plan of action to put forward to the best way to recover that heat. And as plants change and processes change and products come and go and change, the real data inside the facility today is going to be most likely very different than what the design was of the plant. So we need to understand today's reality versus yesterday's reality on how much energy we are using inside the facility. Those are typically unknowns, or at least they're a struggle to find. And those what we try to help you address. We'll do a thermal mapping study, create low duration curves, We want to look at peak load, timing and temperatures, average demand. We want to put together a Sankey diagram. We're going to take a look at where all that energy is used and how much of that energy is used in time, temperature, and loading. And we'll take a look at that in the Sankey diagram. So we do want to get a real understanding of your factory energy requirement. That allows us to better plan what might be the best route to go. It can also help you challenge, as we said earlier, challenge your set points, challenge your OEMs to deliver more efficient equipment. And then we evaluate the waste heat available, okay? What we can do with direct heat recovery, what we may have to do with technologies such as heat pump, and we'll figure that out through a pinch analysis. Then, if there's not enough data available, our engineers that perform these studies will carry with them portable devices that will help us gather the data that we need. And there's a lot of communication, a lot of back and forth between our engineers and the site to drill down as best we can real, concrete, tangible information that we can use to develop the projects. And really, at the end of the day, it's about determining what those ROIs are in those projects and how that affects your CO2 emissions in reaching your goal. So lots of information to take a look at, and we want to use real information. We want to avoid using assumptions to determine this because we want to get to that current baseline and where we're at. And then we'll create a models to predict, simulate different optimizations and decarbonization options. There's typically not a clear choice for every plant. There could be multiple technologies, multiple ways to go about this. We want to show what those are so we can have good conversation with you. You can have conversation internally to figure out where the best way is to go. So in Pinch Basics, we're taking a look at hot streams and cold streams, flows that are being cooled down below ambient temperature, vented through stacks, mechanical cooling, sending to cooling towers to get rid of heat that's dissipated to atmosphere that we're going to take and extract those heat streams to generate a higher grade heat through a heat pump. And the same thing, we'll look at those cold streams. That's the process air that you need to heat. That's the building, the water. It's the water you're using for CIP, for washdown. Those cold streams that are going to need to be heated. And we're going to take a look at the best way to do that with heat recovery, that optimization in mind. And then most importantly, we'll take a look at the pinch temperature, those above and below the pinch. And again, those that would then say, hey, we need to heat, we need to cool, and then find the best ways to do that. So it's really unlocking the full potential of heat recovery and identifying the optimum heat exchanger network between hot and cold. And then really to determine where are heat pumps, and those are technologies that are really good and very useful in helping us through the optimization phase to take a look at those heat pumps. So we'll get heat source curve, we'll get a heat sink curve, we'll combine those together to determine where we can, again, use direct heat recovery, and then where are those points above or below where we're going to need cooling, we're going to need heating, where potentially a heat pump could come into play. So we'll go through and do all these studies. We'll deliver this data to you. There'll be a lot of back and forth. Focusing on the medium grade heaters, those temperatures above 230, above 248, let's say above 250 degrees. And there's a few of those there. We'll look at thermal efficiency best practices. So we know steam's not going away. And there are processes that are always going to be reliant upon steam and the heat that it produces. But we know in generation, we generate with boilers, they're 85% efficient at generation. But many plants are aging, infrastructures are aging, repairs take place. So oftentimes we're left with, and we know we've got inherent losses in piping, in our processes, in our valves, in flash losses. So we know that the amount of heat, or let's say the efficiency of heating, maybe 85% generation at the boiler. It may only be 60% efficient to heat water um, out in the facility through all these losses. So we're going to look at ways to get you back up to improve you to that 80% efficiency. Boiler house optimizations. Certainly that's going to revolve around stack economizers. Steam trap management. Steam trap management is still something that's lacking in a lot of facilities, and perhaps not taken, I would say the word seriously, but not as important as certainly producing product, and we understand that. But that in our decarbonization goal, in our net zero goal, there's waste there that can be easily covered with a very simple and low ROI. So steam trap management is something we need to consider. Insulating our piping. Insulating our piping. Insulating our large valves, those other heat sinks that are going to dissipate energy and make ourselves a little bit less efficient. Flash heat recovery, returning every drop of condensate that we can, and then process heat recovery is certainly something that we want to take a look at. So, we'll look at that in those medium grade users that are still going to use steam. Then we'll take a look at those low grade temperatures, often found in breweries, ice cream, dairies, beverage manufacturers, and so forth. And we want to optimize those through heat recovery and de-steaming, converting those steam networks into hot water. So hot water allows us to get almost near 100% efficiency. We look at heat recovery, carbon capture, CHP, geothermal. Those are going to increase hot water availability for us that we can use. And the way we look at it is that all available hot water must be used to optimize the thermal efficiency. But on the humidification side, many of us have a lot of air handlers, and some of us are using direct steam injection to condition the air in those air handlers. So we can take a look at potentially de-steaming air handlers through adiabatic humidification, and then use heat pumps or other forms of heat recovery to raise or lower, condition the inlet or outlet air from the air handler. And then perhaps probably widely used is partial de-steaming, utilizing many technologies, flexibility of certain fuels to get us to the reality of where we're going to go. And that perhaps could be heat pumps, it perhaps could be a dedicated steam generator for I-grade heat, and then moving to electrical steam generators for specific users. There's not a cookie cutter, one size fits all approach. It's going to take multiple technologies to deliver the results that you want from your roadmap to decarbonization. De-steaming a low-grade heat, we're going to look at heat source, heat sink analysis, the physical time, location, the level of temperature, the amount of heat we have, where that sits in the plant. Are we generating the heat we need or the waste heat we have, but we've got to use it 1,000 feet away? How are we going to transport? How are we going to store it? What does that look like from a piping network? What make more sense for one area to the other? We'll take a look at the heat exchanger network, and this is all part of our thermal mapping pinch exercise, and take a look at those heat sources and heat sinks. We'll look at thermal storage, some of which is current, certainly stratified buffer tanks, perhaps phase change materials getting into the batteries, ceramic materials then in the future to generate heat in one location, maybe even generate heat in one site and store that heat and deliver that heat to another sister manufacturing facility. So all of those things, as those technologies come into play, we will take a look at. And then looking at heat pumps to raise the temperature above the pinch, using the cooling energy as well to help us in our processes and reduce the amount of, let's say, electricity we need to run our motors, perhaps shut down a cooling tower, perhaps shut off or run at a lower percentage our chillers. So industrial high temp heat pumps, taking a look at this, Armstrong does have a relationship with a company called Combitherm. They are out of Stuttgart, Germany. In Europe, we have a joint venture agreement. In Asia and the Americas, we do have a licensing agreement. So we will have Armstrong Combitherm heat pumps. Combitherm's family-owned company, founded in 1972. So they have over 40 years of experience in delivering heat pumps, especially industrial high temperature heat pump packages, into the market. 10-year warranty, but more than 200 heat pumps. That's more importantly, over 200 heat pumps installed with heating capacities up to 2 megawatts. For our Asian friends, Armstrong India, we've been producing heat pumps under a licensing agreement since 2016. In the Americas, done a lot of exhaustive research on heat pumps here. We know that many have been installed. Perhaps those, the technology hasn't been readily adopted for one reason or another, typically because of sizing and installation. But so we've started producing here since 2021. And then Armstrong in Europe produces through the joint venture through Armstrong Combitherm for the European market. So multiple thermal efficiencies, turnkey projects have been done by Armstrong in Europe and in India and through Combitherm, et cetera. So heat pump basics. What are heat pumps? They really use the reverse refrigeration principle, recover low-grade heat to generate higher-grade heat, typically hot water and cooling water for our processes. Typical heat pump COP or coefficient of performance ranges from 2 to 7. The higher the COP, the lower lower the return, or the better the return, I should say. And we're using electricity, so we're using green electricity where available into the heat pump to take that low-grade heat to generate the higher-grade thermal energy out. Temperature ranges typically from 158 degrees up to high temperature heat pumps using R1233 ZDE as the refrigerant up to 248 degrees. And technologies are being worked on and developed now, such as water as the refrigerant, even to generate low pressure steam and even higher temperature hot water in the future. And then we look at cascading heat recovery because we have to keep the COP in mind. And when we're taking a look at through these studies, we're taking a look at the heat sources we have and the temperature profile of those heat sources. And then based on the refrigerant, what type of temperature we can get out of the heat pump where it makes sense and keeps our COP in line with our requirements for our ROI. So if we look at a heat pump, let's say we'll take a 34 kilowatt of electricity in to generate 100 kilowatts of heat out. That alone, if we're taking advantage of just the heating portion of the heat pump, will give us a COP of roughly 3 or 2.94. If I take a look at that then and say I'm going to use both the heating side and the cooling side, that same 34 kilowatt of electricity input will deliver that 100 kilowatt of energy, the heat energy out, the hot, but also deliver to us 70 kilowatts of cooling. So a combined 170 kilowatts of heating and cooling energy, or then a combined COP of 5. Makes it much more attractive, increases the COP, reduces our ROI on the unit itself. So, $1 in gives us $3 of heating energy, $2 of cooling energy to deliver for our system. In all of this, then, is certainly studied, going through and finding the best solution for a given site and for an application. So if we look at it then, how are we looking at this from optimizing this type of a solution? And really, they are going to be sized based upon what our engineers find, because we need true data. We need true input data. We don't need averages. We need to know where that heat sink is and what its requirements are. And we need to be able to match that to size a heat pump to deliver the COP to give you the ROI that you demand. What does it take to do that? We need to monitor those heat sources. That's going to come through from temperature, flow measurement, because we need to ensure, and this is something that we do when we look at it from a packaged standpoint, to where then we guarantee the performance of that package is we have to ensure the process streams we identified, those heat sources, are what they are. And that's what's coming to the heat pump. We do the same thing on the heat sink side. And we need to understand and monitor the flows, the temperatures of what's going to our heat sinks on the hot side and our heat sinks on the cold side. And that's all important to monitor because that's how the optimal efficiency, that's how the COP is going to be calculated. And it's all done based on study of a given area, given portion of the plant, given processes. So the energy metering, the flow and temperatures allows us to monitor the network and to maintain its efficiency. And then we can adapt, we can replace, we can add other peripheral equipment to continue to maintain that optimal efficiency as we go through. So it's more than just saying, hey, deliver me a heat pump. There's a lot that goes with it. There's a lot that'll be packaged with it in order to deliver what you need to meet your goals. So when we look at then another part of the optimization, we talked a little bit about trap management. And some facilities have 20 traps, if I'm talking a food plant. Others in a more heavy industrial, higher temperature, higher pressure systems could have hundreds of steam traps. It's a lot to maintain. Manpower isn't really on the rise inside of our plants. So sometimes we have to do more with less. So how are we monitoring our traps? Most people do perform a steam trap survey once a year. Others do not. Sometimes it's several years in between. So then we take a look at how can we monitor that 24/7 and deliver to you optimum performance on that part of the system. So we've partnered with Everactive, wireless, batteryless trap monitoring to deliver a constant monitoring of our steam trap system, to deliver that to a dashboard on our Sage system that will take into account our wireless monitoring, our manual monitoring, and then take a look at the efficiency of the system. Because we could test a trap today, that trap could fail tomorrow, and then 363 days later, we'll test that trap again. In the meantime, we've lost a lot of CO2, we've lost a lot of energy. So one way to do that is to remote monitor with a wireless, batteryless technology, deliver that to a dashboard that you can use, you can see, that provides you alerts when a trap has failed, deliver reports on how much energy is wasted to help you determine your ROI, and that is flexible enough to allow you to manage that network in the simplest possible way. So once we take a look at that, then we take a look at the end of the day, what are you looking for potentially from a partner to help you with this journey? Perhaps a single point of responsibility might be important to you. That's something that Armstrong in many places can deliver, from the feasibility studies, the thermal mapping pinch, the optimization of the efficiency, the decarbonization of the thermal generation, through the engineering of the solutions, whether it's basic design or detailed engineering and design, coming up with what that solution is going to look like to determine what the ROI is, to perhaps even turnkeying the installation of that solution, or perhaps just providing a turnkey package so that's all encompassing and a plug and play operation for you. So that perhaps is important to you. That's something that Armstrong can take a look at in doing. And then sustaining that efficiency, the Internet of Things, the preventative maintenance contracts, perhaps operation and maintenance of the utilities, performance guarantees, as a service models, where we're financing these improvements over a lifetime of a contract to deliver, say, hot water to you, taking the risks out, turning CapEx requirements as a percentage of the operating expense. So there's a lot of different avenues out there that can help you on your journey to net zero or to decarbonization. And then if you are a global company, perhaps you're looking for someone that can partner with, that can help you on a global basis, scalability, replicability, and again, being able to manage those risks on a global basis. So that's something that perhaps Armstrong can engage with you on in the future to help you down that road. So taking a look at the complete journey towards decarbonization, we're going to take a look at it as from the optimized standpoint, minimization standpoint, and again, finally to the decarbonization standpoint. And we're going to take a look at those technologies right now, today, that are widely applicable. So we'll identify your current state of operating expense, and your current state of CO2 emissions. And then by looking at some of those optimizations that can be deployed, whether it's trap management, whether it's insulation, whether it's direct heat recovery, heat through heat exchanger networks, air to air, water to water, what that looks like in the form of reduction in CO2, reduction of your operating expense, and what that's going to look like as a cumulative CapEx along that particular journey, along that optimization phase, from simple steam system efficiencies to de-steaming with heat exchangers, to de-steaming HVAC with potential for humidification adiabatic, through cascading heat recovery. Yes, there's going to be CapEx requirements, but we're going to show you a pathway that drives down your CO2 emissions, that helps to drive in a positive way your your operating expense to help you become more profitable, more competitive, and then take a look at that relationship as cumulative CapEx along that journey. Then you could take a look at as we're getting into some of the decarbonization methodologies, electrified steam generation, shallow well geothermal, carbon capture, taking a look at what that does, certainly drives your carbon emissions to zero, but how is that affecting then your operating expense? And then what does that look like from a cumulative CapEx expenditure for those particular models? And then into our future technologies, concentrated solar, biomethane, green hydrogen, decarbonized thermal heat in containers, what that might do for you, and give you a picture, give you a roadmap to what might make sense for you in the future. So what we hope to do then is to engage, discover where you are on your roadmap, what are your goals, what are you trying to get to today, by 2030, by 2035, by 2040, how can we help you along that roadmap? And then show you a way to do this that we think, with the optimize, minimize, decarbonize, our circular thermal approach, that might make sense in the future. So that wraps up today's webinar. If there are any questions, and I don't see any questions right this second, but if there are any questions, we'll go ahead and take those now. So we'll wait just a couple of minutes if any of you have any questions you'd like to ask or any comments you'd like to share. It doesn't look like we have any questions coming in. Please, again, Steve Ashby, you have my email address, sha@armstronginternational.com. You can reach me by phone at 269-506-4554. You can comment, ask questions. If you'd like to engage, please reach out to us. We'd like to help you on your journey and help you towards a more greener future with your facilities, and help you become more efficient, more profitable, more importantly, help you produce more products. So if there are no questions, I thank you today for